All right, lecture 03B, efficient stand code and generated quantities. This is basically covering what I just talked about before, but I'll repeat it in 03B. We'll go kind of quickly through this, and then I'll record lectures for next week depending on what's left over. Okay? Okay, by the way, I forgot to mention your homework is not due until October 18th now. I just updated the date on Icon, so don't struggle to get it done by tomorrow. You have 2 more weeks, and Vladimir will be around next week in office hours to be able to help you with that as well. All this will be coming in an email once I know how much I need to record. Okay. Each of this is what I just showed you, but this is the lecture that goes with it to sort of reinforce it. There are ways to make stand syntax much more efficient, right? And part of the ways that we showed just now was that we could use matrices and vectors, or matrix products, and multivariate distributions for priors to help shorten our syntax, to make it a little bit easier to write and to make it a little bit more general. Now, again, I would prefer the following if you're thinking about how to do this on your own. Inefficient, correct code that runs and gives you the right answer is better than super efficient, incorrect code. Okay? We can all agree with that? If you write code that's like beautiful but wrong, it's still wrong. We have a price to pay. We need to have correct code. So write as inefficiently as you need to. As you're starting in stand, I can't encourage you to start inefficient. Right where you know all the parameters, because it gets complicated really quickly. I will also tell you, many students have a habit of trying the most complicated because, they know what they're doing. Me too. I know what I'm doing. I write a complicated code and it won't run or whatever. Well, it turns out complicated code may also have inaccuracies in the code itself, doing things you don't intend it to do. And in a Bayesian model, that can throw the whole thing off. So remember, I'm showing you this because we're going to move that way. But as you're building your code, it's okay to make it very inefficient. It's not a problem. These things run, the linear model version of it runs very quickly regardless. Okay? All right. So if we were to talk about what the matrix version of this happens to be, here's our linear model that I was working with before. We saw this before from the path diagram. But our matrices make it look like this, right? So this is our model predictor matrix. That is our model.matrix result that we talked about before. And here's the first set of 6 values for it. We have 6 coefficients, beta 0 through beta 5. So the matrix product of x times beta would take each row of x, multiply each element by the corresponding element of beta, and sum them together. Right? So we can shorten our notational syntax by saying weight in pounds, which is a vector, is equal to x, our design matrix, times our coefficient vector beta plus error. Now I want to make a few distinctions. Again, matrix algebra, I don't believe many of you have taken it, and if you have, that's great, but let me talk about to those who haven't. A vector is a matrix where one of the dimensions is size 1. That's how we define it. A matrix is like a box of data, right? Where there's potentially n rows, p columns, and each combination of n and p, right? Each element of it has a number in it. So it's a way of storing data, right? Like this. So a matrix like this vector right here only has 1 column. So we call it a vector. Turns out a vector is a matrix, right? A matrix has 2 dimensions. A vector technically has 2 dimensions. Sometimes we call them row vectors, right? Where there's multiple rows but 1 column. Multiple columns but 1 row. And sometimes we call them column vectors, right? Where there's 1 column and multiple rows. But this right here is how we condense all of those terms into a matrix. And so if we want to talk about predicted values, again, this x right there, our design matrix, 30 by 6, contains all of our predictors for every person. When we multiply it by a vector of coefficients, let's say those are the posterior means right here, we get the predicted value for each individual in our data set. So x times beta is a shorthand for calculating lots of values all at once. So again, we saw how this changed, right? In our data section before, we had vectors, but each one of those vectors had our predictor values in them. We've replaced those with a design matrix, X. That is n rows by p columns. Right? So in the matrix bracket, the first term is the number of rows, the second term is the number of columns. Right? A vector, which we saw before, is implied to be a row vector instead, meaning it has n rows and one column. Sorry, excuse me, I keep getting it wrong. It's column vector, one column. A bunch of rows in one column. Sorry. All right, so the parameters themselves as well can be, we can use matrices for parameters or vectors for parameters. So here beta is just a vector, whereas before we had to declare every single beta in our model. And again, the benefit to doing this is if we change our model specification, we change how complicated our model is, we don't have to change our stand code. Right? We can always make it build the way we want. Right? So here I mentioned the prior distributions also. Right? So we can use vectors and matrices for priors. We could use previously we used univariate normal. But in this last bit of code, we use a multivariate normal. If you wanted to see what multivariate normal distribution looks like, it looks like this. It's a series of univariate normal distributions. Right? Multivariate normal, if you haven't learned it before and you're learning statistics, I strongly recommend you go study just the multivariate normal. It shows up in almost everything that we do somewhere. Right? And it also shows up in asymptotics. So like if you have multiple parameters, if you want us to describe their behavior as n goes to infinity, turns out multivariate normal is involved in that as well too. But I'll leave it to you to do that. That just means what I had told you in the syntax is true. We need to put all prior means into a vector that's size p rows by one column. And then we need to put all prior variances, right, the squared standard deviations, into the diagonal of our covariance matrix. And that covariance matrix should be size p by p, number of predictors by number, number of coefficients by number of coefficients. And I set the zeros for the off diagonal. I set them to be 0 on purpose because it allows those to be independent, and I don't have a prior belief about how things should covary. If we have time at the end of this, I'd be happy to add a non-zero element to this to the off diagonal, and you can tell me if it changes things. Okay. Okay. And again, you can see the changes. Previously, we had to specify every coefficient with its prior distribution, and now it becomes the whole vector itself. So I find this a lot easier to be more general. Sigma still has its own line, though, because sigma is a separate parameter with a separate prior distribution. We could probably find a way to lump it into the other one as well, but let's not go there yet. Okay? Questions so far? Okay. So, with matrices, there's a lot less syntax to write. The model is also equivalent. So when we build a model with matrices versus a model without, the model is the same. It's just made a little bit differently. The bigger problem, though, is that our output is not labeled, right? So it's beta 1 through beta 6. That is a bit of a problem, but if you can keep track of your labels, it's fine. In the model matrix function in R, here, if I look at X, what do I call it here? This term right here, if I put these will be the names of the coefficients. So the column names of the predictor matrix are the names of each of your coefficients, 1 through 6. So if you wanted to figure out what those happen to be, that's how you do it. Sound good? Okay. And I realize with this, my contrast vector is incorrect. I added the 4th coefficient. I really should have added the 5th. It seemed wrong when I look at it. Let's rerun it real quick. And now let's look at the trace plot for it. Maybe I didn't. Oh, you know what? I didn't change my stand data. That'll do it. No, maybe I didn't do it wrong. Anyway, I'll leave it. Yeah, it's a little moved over. Anyway, my bad. All right, the computation of parameters can be done pretty quickly in R as well too. Linear models always have some type of other things we compute. Missing effects, such as the slope for diet group 2. Simple slopes, which is when you're trying to talk about the value of a slope when the continuous variable is at a certain level. So for instance, what's the mean difference for people who are height 72 inches, 6 feet tall? R squared. You go down the list of things you can calculate with this. In non-Bayesian analyses, these are often formed with point estimates of parameters, but what we're going to do is build a posterior distribution which takes each draw, what I mentioned, those posterior sample draws, and calculates them for each successive iteration from the algorithm. So this example with diet group slope group 2 is what I was building before. We discussed how to find that here. And we can see where the values happen to be. And again, I've been calculating it wrong here. I needed a beta in the 5th position. My calculation was 2.10. That's what 2.10 was the slope for group 2. There it is. Yeah. This is what I've done here to show you this is the sum of the way to do it at the end. This is if you have take the draws from group 2 and add them to the draws from group 5 or number 5, and you get that posterior distribution there. Generated quantities is how to really build this more directly. And that's with the contrast matrix that we see here as well too. And our code I showed you before as well. Similarly, R squared, here's your regression sums of squares and your total sums of squares. This is what I was telling you about previously. I hate that the markdown quarto moves the hat over. So sorry about y hat being moved over. There is a command to fix it, and I've forgotten what that happens to be. And I also hate that my slides aren't displaying the right size on here. Sorry about that. Anyway, and we can build R squared in there too. So that is the end. That's our lecture. Our example, our generated quantities. If I were to describe what comes up next, let me do that real quick. Let me go to our GitHub repo. Lecture 3C is where we talk about how we compare models, how we determine which prior distribution might be better than others. And in Bayesian methods, sort of calculating ways to go and say, hey, this model seems to fit a little bit better than the other one as well too. So what I will do in our next meeting, actually, once again, next week, no class at class time. Again, this will be coming over an email, so you're all familiar. I will record lecture 3C prior to next week. Your job is to watch it and work on homework. And I will tell you, the homework may take some time, may take some effort. But everything that I showed you today with the syntax is pretty close to what you need to do the answers for the homework. Most of what you can do for the homework is done today, but then there'll be a model comparison that we'll have to talk about, I think, as well. So, another question in chat. Just to follow up our variation question, what I mean by least square is that LM uses least square estimation. They are looking for one best linear combination equation. So there's no variation in R. Is that correct? Right. In LM, the least squares estimates that you get from LM do provide just the best estimate of R squared. So there won't be variation to it. Technically, you could compute like what we would call an asymptotic variance for R squared, and people have computed that as well, but we never talk about that very often. But yes, the least squares estimates in R, if you use the LM function, will give you the best fitting R squared overall without variation to it. Did that answer your question? Thank you. We have a few extra minutes. Any other questions? Again, I cannot encourage you enough to ask questions. I'm trying to break down every barrier I can to make sure it's easy to ask questions. I respect all of your questions. There is no such thing as a question too simple. Maybe a question too complex, but you'll just get an answer that says, I don't know. But that's fine. All right. Well, if there's no other questions, how about we stop here? Thank you for your time today. Be on the lookout for an email informing you about when to watch Lecture 3C, which will be posted sometime in the next few days. Again, no class next week. So, thank you all. Good to see you. And enjoy the Bayesian between now and then. Have a good rest of your day, rest of your week too. Take care.